Hello my dear students, I welcome you all for this lecture. So we are discussing the chapter number 13, that is nuclei. So we will study the expression for half-life. Okay, so we should consider the previous expression, okay, that is the relation n is equal to n naught e raised to minus lambda t. Suppose that is equation number 1. Here we're explain the half-life. Okay, so here for the nucleus, okay, so suppose you should take the full nucleus. Okay, so that is having, suppose the n naught is the initial number of atoms in that radioactive substance. So you know that what is meant by radioactive substance. So these are the heavy substance and that will be emits continuous radiations. Okay, so that will emits continuous radiations. So here we'll consider the for whole atom. Okay, n naught will be the initial number of atoms, okay, in a that radioactive substance for the time 0. Initially it is time 0 for t half. Okay, for half life, for t half, so you should take the n naught by 2. Okay, so it is the for t it is n naught, for t half n naught by 2. Okay, so suppose in this equation the n is equal to n naught e raised to minus lambda t, where n naught is the initial number of atoms in a radioactive substance and n is the number of atoms at given instant t. Okay, so n is what? The number of atoms at a given instant t, and lambda is the decay constant. Suppose the lambda is a decay constant, this lambda is, then for half life period the t is equal to t half and n is equal to n naught by 2. For the half life period we'll take the equation number 1, n as a n naught by 2 and t as a t half. Therefore, the equation 1 becomes n naught by 2 is equal to n naught e raised to minus lambda t half. Okay, so therefore the n naught by 2 is equal to n naught divided by e raised to lambda t half. Okay, e raised to minus is there, you should take for denominator as a e raised to lambda t half. Therefore, the e raised to n naught get cancelled. So here you should take 2 is equal to e raised to lambda t half. Okay, by solving this equation, you will get e lambda t half is equal to 2. But according to the log theorem, okay, logarithm theorems, the e raised to x is equal to y. If e raised to x is equal to y, then x is equal to log y to the base e. Therefore, lambda t half is equal to, here you should take the lambda t half is equal to log 2 to the base e. Okay, instead of here x, e raised to x, here the e raised to lambda t half is there. Okay, so y as a 2. Therefore, the x means here in this equation lambda t half is equal to log 2 to the base e. Therefore, the lambda t half is equal to, okay, this is a 2.303 log 2 to the base 10. Okay, for base 10 you should consider like a 2.303 log 2 to the base 10. So therefore lambda t half is equal to this value 2.303 into 0.3010. Okay, by multiplying this one you will get 0.693. So the t half is equal to 0.693 divided by lambda. So this is the expression for the half life. Okay, the expression for half life is the t half is equal to 0.693 divided by lambda. So I repeat. So you should consider the previous equation, n is equal to n naught e raised to minus lambda t, where n naught is what? The initial number of atoms in a radioactive substance, and n is a number of atoms at given instant t, and lambda is a decay constant. Okay, for half life period, the t is equal to t half and n is equal to n naught by 2. So this equation 1 becomes, wherever t is there you should put as a t half, and n is there you should put as a n naught by 2. Therefore equation 1 becomes n naught by 2 is equal to n naught e raised to minus lambda t half. So therefore n naught by 2 is equal to n naught divided by e raised to lambda t half. So n naught get cancelled, and 1 by 2 is equal to, you will get 1 by e raised to lambda t half. By solving this you will get e raised to lambda t half is equal to 2, but according to the relation e raised to x is equal to y, this is the equation for logarithms. Okay, so if e raised to x is equal to y, then x is equal to log y to the base e. X is equal to log y to the base e. Therefore, lambda t half is equal to log 2 to the base e. Then the lambda t half is equal to, so by solving this you will get the e base is there. If you want to take as a log base as a 10, you should multiply 2.303 into log 2 to the base 10. Therefore, the lambda t half is equal to 2.303 and log 2 to the base 10 value is 0.3010. By solving this, you will get lambda t half is equal to 0.693. Therefore, t half is equal to 0.693. Lambda take this side, that is divided by lambda. Therefore, t half is equal to 0.693 divided by lambda. This is the expression for half-life. So next, we will derive the another expression, that is the expression for mean life of radioactive substance in terms of decay constant. Okay, in terms of decay constant, suppose the mean, okay, time, the mean t, the Tm is equal to, suppose the total life time of n naught atoms divided by the total number of atoms as a n naught. Okay, the Tm is equal to, we'll write T by n naught. Okay, T is a total lifetime of n naught atoms and the total number of atoms as a n naught. Okay, so if n naught is the, we know that the another relation, n is equal to n naught e raised to minus lambda t. Suppose this is equation number 2 and Tm is equal to T by n naught, that is equation number 1, where the n naught is what? N naught is the initial number of atoms in a radioactive substance at time t is equal to 0. And n is what? N is the number of atoms present at a given instant t. Let Dn be the number of atoms disintegrated during the time interval dt. Okay, so if the disintegrated, then nuclear decay. Okay, so nuclear decay will form there. Okay, so that is the disintegration of the radioactive substance will be, okay, so that is for dn number of atoms at time interval dt using decay law, that is dn is equal to minus lambda n dt. Dn is equal to minus lambda n dt. Suppose that is equation number 3. Since dt is what? The very small, we have assumed that all these dn atoms have lived for a time t. Okay, so since dt is a what? It is a very small assumed the atoms, okay, all these DN atoms, okay, that are lived for a time t. For a time small time t, suppose the DN all atoms, okay, will be lived in that. Therefore, the total lifetime of all the DN atoms is what? T into DN. Okay, so that is T is a all atoms time lived in that and into Dn. Okay, Dn is the assumed all amount of atoms. Then the total life of time of an atom between the limits at n is equal to n naught to t is equal to 0 and n is equal to 0 to t is equal to infinity. Therefore, the t is equal to, suppose the integration n naught to 0 t and dn, suppose that is equation number 4, that is changing the limits of integration in terms of time, then the equation 3 and 4 becomes the t is equal to integration, okay, that is 0 to infinity, at t is 0 to infinity into t lambda n dt. Suppose that is equation number 5. From equation 2 and 5, okay, you should put the values, okay, that is from equation 2 and 5, the t is equal to integration t is equal to 0 to t is equal to infinity lambda n naught e raised to minus lambda t dt. Therefore, the Tm is equal to, suppose the integration, the t is equal to 0 to infinity t lambda n naught e raised to minus lambda t dt divided by n naught. Okay, therefore the lambda that equal to lambda into integration at t is equal to 0 to t is equal to infinity t e raised to minus lambda t dt, where the lambda, you should solve this by integration. So that is the t e raised to minus lambda t divided by minus lambda at 0 to infinity minus integration 0 to infinity e raised to minus lambda t by minus lambda dt. So this is equal to, so this value will be 0. So 0 plus e raised to minus lambda t divided by minus lambda at 0 to infinity. Therefore, the Tm is equal to 1 divided by lambda e raised to minus lambda t minus e raised to minus lambda into 0. Okay, so that is the 1 by minus lambda, that is 0 minus 1. So that is 1 by lambda. So Tm is 1 by lambda. So therefore, the Tm is what? It is the mean life of radioactive substance in terms of decay constant. Okay, so that is Tm is equal to 1 by lambda. So next, we'll study the relation between half-life and mean life. Okay, so we know that the half-life is T half is equal to 0.693 divided by lambda. Suppose that is equation number 1. And the mean life period is Tm is equal to 1 by lambda. That is suppose equation number 2. So we may take equation 1 divided by 2. So that is T half by Tm is equal to 0.693 divided by lambda into lambda by 1. So lambda and lambda get cancelled. So remaining term is only 0.693. Therefore, the T half is equal to 0.693 into Tm. Okay. Therefore, the mean life of a radioactive substance is always greater than its half life. Okay, the mean life is always greater than half life. So this is also the important relation, that is T half is equal to 0.693 into Tm, where T half is what? It is a half life period of radioactive substance and Tm is a mean life period of radioactive substance. So the we'll take the additional information, that is what the number of atoms present after n half leaves, then the n is equal to n naught divided by 2 raised to n. Suppose the number of atoms present after n half lives, then the n is equal to n naught by 2 raised to n. In terms of masses, that is m is equal to m naught by 2 raised to n, and in terms of activity the A is equal to A naught divided by 2 raised to n. Then when the n half leaves, the total time, if the T is equal to nt, where the n is a number of half leaves and T is what? The half life period. So therefore the T is equal to total time for that half leaves will be T is equal to n into T, where n is what? The number of half leaves and T is a half life period. The next one, the half life, mean life and decay constant are independent of the number of nuclei present. External factors like pressure, temperature, etc. It does not affect on the elements. Okay, so therefore it is a nature of here it is depends on the nature of elements, and for a given element is a it is a constant. Okay, so see here for the half life and mean life. Okay, for the decay constant they are independent. The number of nuclei are present. External factors like pressure, temperature, etc. that will be depends on the nature of a element. So suppose if it is a heavy element, okay, so therefore the nature, the factors like pressure and temperature will be not effects, but if it is not a heavy element, then it the effect will be there, like this. The here the relation between the half life and mean life we studied. Okay, next one, that is the nuclear decay. Okay, so first, before going the alpha decay, we will see the nuclear decay. Okay, so nuclear decay means what? Okay, the alpha decay, the gamma decay, and the beta decay. These are the three types of the nuclear decay. So first, what is meant by the nuclear decay? Decay means it is a disintegration. Decay means what? It is a disintegration. So if the heavy nucleus like uranium continuously emits the special kind of radiations, this process is known as what? The nuclear radioactive element. And the heavy elements like uranium are known as the radioactive elements. Okay, so the process is known as what? Radioactivity, and the elements like uranium, heavy elements are there that are known as radioactive elements. Then the radioactive elements are having three types. That first type only the alpha decay. Okay, so what is meant by the alpha decay? Okay, we will explain with examples. So it is the process of emission of helium nucleus during the nuclear disintegration. So if the element of any nucleus during radiation time, if emits the alpha particle and transfer itself in the another form of element, so that type of element is known as what? Alpha particles. Okay, so alpha decay, or that are the alpha particles. Okay, when a radioactive element emits a alpha particle, okay, like uranium, for example, the uranium is a heavy element and it will continuously the gives the some emits the radiations. Here that emission of alpha particles, its atomic number decreases by 2 units and mass number will be decreases by 4 units. So in generally we'll say, suppose the x z to a for the alpha part decay process, that is z minus 2 y a minus 4 plus helium 2 4. Okay, so here the helium is a alpha particle, and suppose the x is a, suppose the parent element, and y is a daughter element. Okay, it is a daughter element. For example, suppose uranium 92, uranium 238, whenever go through the alpha decay, then the thorium 90, thorium 234 plus He24. Okay, so that is a equation or example for the alpha decay. So here see the 92 will be like 90. Okay, therefore Z is Z minus 2, and 238 will taken as a 234. So that is A as a minus 4. Okay, plus the He4. Okay, here if it is minus 4, obviously the remaining will be goes through the alpha particle. Here helium is alpha particle, therefore helium is, suppose, the 2 helium 4. This is a one example for alpha decay. Then we'll see the disintegration energy or Q value of a nuclear reaction. Disintegration or Q value of nuclear reaction. It is the difference in the initial mass energy of radioactive substance and the total mass entry of the decay produced. Okay, so the disintegration energy, okay, or the Q value of nuclear radiation, and here suppose we'll take the uranium 92 to 38 and the alpha particle, suppose the thorium 90 to 34 and plus 2 helium 4. So this is a, suppose, the main equation for it for the alpha decay. Then we'll study the disintegration energy of Q value of a nuclear reaction. It is the difference in the initial mass energy of radioactive substance and the total mass energy of the decay constant. Okay, so suppose we'll see the Q factor. Q is equal to mx minus my minus m alpha into c square, and c square is E is equal to mc square. Okay, using that equation we should find, and mx is what? It is the mass of the parent nucleus, My is the mass of the what? That is the daughter nucleus, and M is the mass of the alpha particle. But the here the mx is what? The mass of the parent nucleus, My is the mass of the daughter nucleus, and the Ma is the mass of the alpha particle. Then we'll see the note. Okay, during alpha or beta particle decay, okay, the total mass of the products is slightly less than the total mass of the reactions or the reactors. Then the difference is the mass will be converted into the energy, which will be the energy to the net kinetic energy gain in this process, and it is a nucleus for X is at rest and Q is in kinetic energy gained in a process by the product nucleus and the alpha particle in the above relation. If the masses will be atomic mass unit, then the equation becomes the Q is equal to mx minus my minus ma into 931 MeV. Okay, so that is the value Q for Q factor, that is Q is equal to mx minus my minus ma into 931 MeV, mega electron volt. So here the if the heavy nucleus can be only be emits the alpha particle. Okay, like uranium only emits alpha particle. If the Z will be greater than the 83, then only it performs this kind of decay. Okay, if the Z is greater than 83, only the performs this kind of alpha particle, and this process is spontaneous due to the greater mass of parent element. Okay, due to the greater mass of parent element, then energy Q value is Q is equal to mu minus m th minus m alpha into c square. Okay, so that is the Q factor. The Q value will be mx minus my minus m alpha into 931 mega electron volt. And the position is an elementary particle. It is the antiparticle of electron in the mass that is equal to the mass of the element and having the positive charge equal to the charge on the electron. Okay, so like this the alpha particle is covered. So next second one, okay, that is a beta particle. So what is a beta particle? It is the process of emission of another, okay, or either an element or a particle during the nuclear disintegration. Okay, so suppose the process of emission of either an element, okay, of a position during the nuclear disintegration. For example, you should take the negative beta decay and the positive beta decay. Okay, suppose the during the relation, okay, during the nuclear relation, or the nuclear reaction. So whatever the energy will be comes out, that is in form of electrons and positrons. Okay, and electrons and positrons are the both are what the antiparticles of each other. Okay, therefore the electrons and positron are the antiparticles of each other. When electron releases, it comes out with the antineutrino. With the antineutrino. So here when the position comes out with the neutrino, then the antiparticle is equal to, that is antineutrino plus neutrino. So these are the very small particles and as compared to the element. Okay, so for the negative beta particle, beta decay, it is the process of emission of an electron during the nucleus disintegration. During this process, the mass number of daughter element remains same and the atomic number increases by 1. For example, suppose the X ZA, the negative beta decay, Z plus A YA plus E minus 1 0 plus the here that are the alpha particle. Okay, so like this, for this is known as, for negative beta decay, it is known as neutrino, anti-neutrino. Okay, for negative beta decay, it is known as anti-neutrino. For example, you should take the here, that is the 15 phosphorus 32 gives the 16 sulfur 32 plus minus 1 electron 0 plus gamma bar, that is a anti-neutrino. Here in this equation, the daughter element, okay, the that is having the atomic number, okay, that will be increases by 1. So it is here 15 and it is 16, and as compare with the parent element, there will be daughter element is having the number of atomic number will be increased by 1. Then the antineutrino is emitted during negative beta decay when inside the nucleus whatever the electron is found due to the conversion of the nuclear into the problem a proton and electron and antineutrino. The reaction is given below, like neutrino is equal to proton plus neutron plus that is gamma, where gamma bar is a antineutrino and gamma is a neutrino only, and which part emits along the electron when a converted into the proton in a nucleus. Okay, antineutrino. Then after that we'll see the next slide. So what is meant by positive beta decay? So positive beta decay, it is the process of emission of positron during the nuclear disintegration. During this process, the most number of daughter elements remain same and the atomic number decreases by 1. For example, XZA is equal to, that is the position of beta decay, and y z minus 1 a plus minus 1 E0 plus gamma, okay, where the gamma is a neutrino. Therefore, for example, that is Ne1122, the positive beta decay, that is the Ne1022 plus electron plus 1 0 plus gamma, where it is a gamma is what? That is a neutrino. For positive beta decay, the gamma you take as a neutrino. For negative beta decay, you take gamma as a antineutrino. Explain how the neutrino is emitted during the position beta decay. Inside the nucleus, suppose the positron is formed due to the conversion of proton and neutron, electron and neutrino. Then the here suppose you should take the proton is equal to neutron plus positron plus gamma. But it is a gamma is a neutrino, and it is as compared to the proton and neutron, it is very small. So therefore it is negligible also. Which particle emitted along with the position when a proton is converted into the neutron in a nucleus? So neutrino is a particle, okay, that emitted along the position of proton, and that will be converted into the neutron in a that that is neutron in a nucleus is neutrino. So neutrino is a particle. Then what is a gamma decay? Explain with example. So gamma decay is what? It is the process of emission of photon during the nuclear disintegration. Nuclear disintegration for X Z A, for beta decay ZX4 my plus gamma, where gamma is what? It is a photon. For example, the gamma decay is what? It is the process of emission of photons. Okay, so gamma decay is not like the material like alpha and beta, but the gamma is a electromagnetic waves. Gamma is what? They are the electromagnetic waves, and nucleus is having suppose energy levels like atoms also. Okay, so nucleus is also having energy levels like atoms. If we will go through the higher energy level to lower energy level, then whatever releases, okay, and plus the energy will be releases in mega electron volt. So therefore the example for gamma decay is C02740 negative beta decay, and that is 28 Ni60. So 27 to 28 1 you should increase, and here you are taken minus 1. So it is balanced. So this is the equation for negative beta decay, and for positive beta decay it is a N28 to 28 N60, that is the gamma decay, and plus 28 Ni60. Yeah. And here the gamma is a photon in this sheet, and the C27CO60 is a radioisotope. 28N60 is a nickel in excited state. Okay, it is a nickel in excited state, and Ni2860 is the nickel in a ground state. So like this we will study the beta decay. Then in this chapter we will solve some numerical problems for next video, and for numerical problems these are the important formulas to find the binding energy, binding per nucleon and mass defect of a given nuclei during the given mass. Okay, given data is, that is the formula used, delta m is equal to ZMP plus A minus ZMN minus M, and binding energy EB is equal to delta M 931.5 mega electron volt, and the binding energy per nucleon is that is EB by A. And the another one formula to find the half-life and mean life and decay constant of a radioactive sample. Then the formula will be, suppose lambda is equal to the R is equal to lambda n, and T half is equal to 0.693 divided by lambda, and mean life is 0.66144. And here we'll see, that is the activity of sample R is equal to lambda n, T half is equal to 0.693 divided by lambda, and the mean life is that is tau m or Tm is equal to 1 by lambda, and 1 Ci is equal to 1 Curie is equal to 3.7 into 10 raised to 10 becquerel. So with this I conclude my speech. Thank you. Thank you one and all.